Kia ora and welcome to question 1 of the 2009 Scholl Calc exam. This question has 3 parts to it. First part is a differential equation that's related to simple harmonic motion. 1b is a cycloid, which we're given the parametric equations of, and then we're asked to do stuff with its acceleration. And then lastly, we've got a complex number equation there, of which we need to use some trig identities to prove that u over v is equal to cotan of 3 theta. Alrighty, question 1. This is an example, a very typical example, of where you're given the solution to a differential equation and all you need to do is verify that that solution is indeed a solution of the equation. So we don't need to integrate, we don't need to solve the differential equation using things like separation of variables or anything. We just need to substitute the solution into the differential equation. Okay, so if we go left-hand side of the differential equation, which is the second derivative of y with respect to x, then we just need to take our solution that we're given and differentiate it twice, and then prove it's equal to negative k squared times the solution itself. See on the right hand side there, the solution appears again. Okay, so we need to find the second derivative of this thing. And if you know anything about trig functions, when you add two trig functions that have the same period, in this case we've got kx in the inside and the frequency is k, it doesn't matter that the amplitudes are different, one's a, one's b, but if you add two trig functions with the same period, you just get a trig function. And if you know anything about simple harmonic motion from physics, where the acceleration, is this acceleration? If we change the independent variable, which at the moment is x, if we changed it to t for time, and same in the solution, then we would get a trig solution to the equation, and the left-hand side would represent acceleration. It'd be proportional to displacement, and that's what simple harmonic motion is about, where the acceleration is something like a spring or a pendulum is proportional to the displacement. The further it gets away from the middle, the more the restoring force. Okay, so let's take our solution, a sine of kx plus b cos of kx, and differentiate it once. So sine goes to cosine, but we've got the k on the inside there, so we need ak cos of kx. Cosine goes to minus sine, so it's minus bk sine kx. Okay, and then differentiate it again. Remember that k is a constant here, so ak in front is just a constant. Cos differentiates to minus sine, so we've got minus, be very careful here, we have ak squared, because we get an extra k using the chain rule, sine of kx. And then sine differentiates to cosine, so it's minus bk squared cosine kx. And we can factor out the minus k squared here. And then we're left with a sine kx plus b cos kx, which was indeed our solution for y. Okay, so left-hand side equals the second derivative. We needed to prove that it equaled negative k squared y. Oopsies. Negative k squared y, and that indeed equals minus k squared y. So we've proven it. Okay, second equation here. Before we start on this problem, I actually want to show you a little animation that I found on Desmos for this, and then I'm also going to derive these equations. Okay, it gives you the parametric equations, and it's likely in a scholarship exam that they would give you those. If they wanted you to derive them, if you weren't able to do it, you can't solve any of the problem. So it's likely that they would give you these equations. But let's first up look at Desmos. I'm just going to slide this back here to 0. Okay, so at the start where the circle is centered on the y-axis, point there which is rolling is right at the top of the circle. And you might see that the equations are a little bit different to the ones that were given in the exam paper, because we've got AT inside the sine and the cosine, and also at the front. So wherever there was a t in the equation, it's actually AT, and that's just to get the circle to move. So if I was to rotate this to 1, see, it's kind of hard to do. Notice that the circle now is centered at 1, and the blue curve, which is the cycloid, is only being drawn up to t equals 1. You might not be able to tell, but when we rotate this around to 2, it's a little bit, like even 3. See 3 there, it's very, very close to the bottom of the circle. It's at the bottom of the circle when it gets to pi. So at a equals 2, the circle is centered at, stop there please. Good. The circle's centered at 2 there, but this point, the coordinate of it is now 2 plus sine of 2, 1 plus cosine of 2. And again, the cycloid's only drawn to t equals 1. It's drawn from t equals 0 to t equals 1, and the point is at the end of it. So, that's where t equals 1. And if we've got a is equal to 2 times 1. So the coordinate there is 2 plus sine of 2, 1 plus cosine of 2. Now, could we have derived that from a diagram? And of course, if it's got trig in it, then it's just stuff to do with triangles. So let's have a look. I've taken the snapshot of that, where a is equal to 2. Now if I just go down the middle of the circle for a start, that of course is y equals 1. And then at the moment the circle is centered at a is equal to 2. If I draw a right angled triangle there, what you need to realize, which isn't necessarily obvious, is that this angle from here all the way around to there is equal to t. Did I say t? I mean, in this particular diagram, it's a. A is 2. 2 radians is just a bit bigger than 90 degrees. Pi over 2 is 90 degrees. So the coordinate, if we want this coordinate xy here, then the x value of that coordinate is 2 to get us from the origin out to the center of the circle, plus, what's that distance there? Okay, so what is that distance? Well, if the angle, I'm telling you the angle from the vertical all the way around is a, then the angle in the triangle there is pi minus a. And therefore the green part is sine of pi minus a, because the hypotenuse is the radius of the circle, which in this case is 1. So our x value is the 2, or in this case a, plus sine of pi minus a. And sine of pi minus a, if you draw it, it's actually just the sine of a. The pi minus bit is like a reflection and a shift. So that actually just equals a plus sine of a. Similarly, for the y value of that point in orange, in that case it's the center of the circle is y equals 1, and that's always going to be the case. It's not moving up or down, it's just rolling along the x-axis. Plus, actually no, not plus, minus this dude. So we take 1 and we minus off the cosine of pi minus a, and the cosine of pi minus a is the negative of cosine of a. If you're not sure about that, you either graph it, so like I graphed that and I graphed that and see what the graphs are, or you can use the compound angle formula for sine and for cosine that is on the formula sheet, and you get a whole things of zeros because sine of pi is 0. Okay, so if we do that, we've got 1 plus cosine of a, and then as I had confusion earlier, if we just change all the a's to t's, we get the equations that were in the exam. Okay, so that's how you would, I guess, derive them if you needed to, but the question, like most SCOL questions, will just give you the equations to start. Okay, what do we need to do with these equations? We've got an equation for the speed of the point, and it looks like Pythagoras there, and we're talking about speed and not velocity. And then the scalar acceleration of the point is given by the derivative of that speed function. Find and simplify an expression for it, and find an expression for a of t as well. Show that a of t is not continuous. Okay, so take our equations to start. The first mark is probably just for substituting these equations into the expression and doing something with them. So if I substitute into the speed equation, I need to differentiate both of these. dx dt is equal to 1 plus cosine of t, dy dt equals minus sine of t. I need to square them. Okay, we're subbing into this thing here, so I need to square these, add them square root. So s of t square root 1 plus cosine of t all squared plus minus sine of t all squared. When square roots are involved, you hope that the thing underneath the square root is a perfect square, because it will simplify if so. And when trig expressions are involved, you know, you've got sine squareds and cosine squareds. You know that sine squared plus cosine squared equals 1. So if we expand the first one, get that. And if we expand the second one, we get that. And then we've got the sine squared plus cosine squared t thing there. So we're square rooting 2 plus 2 cosine of t. And you can pull the 2 out of the square root if you wanted. It's a common factor there. If you do so, you're going to just get square root 2 out the front. So if you look at your formula sheet, there is some stuff to do with cosine squared. There's a formula on the formula sheet, the double angle formula, which involves perfect squares. So if I rearrange this equation, I've got 1 plus cosine of 2a equals 2 cosine squared of a. And then if I double everything in this equation, I've got 2 plus 2 cosine 2a equals 4 cosine squared of a. And then it's what I've got underneath the square root there. As I was saying, we're looking for perfect squares. And the only difference is the angle. The fact that the angle here is t, and we're dealing with one that's got 2a. So by rearranging this, it's like a half angle formula. So I can square root So I can square root 4 cos squared t over 2, and write that as 2 cosine t over 2. Assuming that cosine of t over 2 is positive, otherwise we need absolute value symbols there. So we better put them on, because if you square root x squared, it doesn't just equal x, it equals plus or minus x, depending on the sign of x. So that's our expression. We actually didn't need to do that. We could have stopped at the point here, and that would have been enough to solve the next problem. Okay, find an expression for the acceleration and hence show that the acceleration is not continuous. So if we'd stopped at the point where I put the asterisk, we would just need to differentiate that. But since we're there, s of t is equal to plus or minus 2 cos t over 2. So if we find acceleration, depends on if we take the positive or the negative. If we take the positive, then it differentiates to minus 2 sine t over 2 times a half, chain rule, minus sine t over 2. If we take the negative root, acceleration is equal to positive 2 sine t over 2 times a half equals sine of t over 2. And these expressions are not continuous. When you think about where the plus or minus kicks in, you need to think about the argument of this thing. Like if it's positive, then the absolute value symbols aren't needed. If it's negative, the absolute value symbols are needed because it turns them into a positive quantity. So if you think about the cosine of t over 2 graph, I'm going a little bit beyond what the question needs here. But if you think about that, it's a cosine graph like normal, but it's got a frequency of a half. A normal cosine graph would stop at 2 pi, the one whole cycle in 2 pi. This one here takes twice as long to get to the end of the cycle, so therefore that's 4 pi. And there's different regions where it's positive and negative. So up to pi, it's positive. So the acceleration formula is the first one, minus sine t over 2. And then it switches after pi all the way up to 3 pi to be the other function. So what's happening as t approaches pi? The acceleration formula, the top one approaches negative sine of pi over 2. Okay, and that's negative 1. So as t approaches pi, a approaches negative 1. And then the other one, as it leaves pi, as t, I'm not going to say approaches pi, but increases from pi, the acceleration, I think, increases. Actually, no, there's a better way of saying this. As t approaches pi from the positive side, so in other words, going backwards in time, then the acceleration would approach positive 1. And they're clearly different values, so it's discontinuous. Now, I don't expect most people would have answered it that way. They probably would have gone to where I stopped with the asterisks and just taken that equation there. And that's probably easier. So if we take that, s of t equals the square root 2 plus cosine of t. Okay, now that equation there, so we're missing a 2. That equation we simplified because we realised the double angle formula helps us to turn it into a perfect square. But if we're there and we want to find acceleration, we just differentiate that expression. Okay, so rewrite that as 2 plus 2 cos t to the half, differentiating half comes down the front, 2 plus 2 cosine t to the minus 1 half, multiplied by the derivative of the inner function, which is minus 2 sine. Let's simplify this a little bit, the 2's cancel. We've got minus sine on the top, divided by the square root of 2 plus 2 cosine t. And it's enough to say that this is discontinuous when the function is undefined. And that's when the denominator equals 0. So if we consider values of t where this expression here equals 0, a is not continuous when 2 plus 2 cosine t equals 0. Rearranging that equation, cosine t is equal to negative 1. Again, think about what the cosine graph looks like. This time it doesn't have a 2t in there, or a half t, so it's going to 2 pi. Negative 1 is here, and that's at pi. So when t is equal to pi, which is the discontinuity we had before, at this point here where the speed function went from positive to negative, and then the absolute value symbols kicked in. And the other one, of course, is at 3 pi. It gets back to the next minimum. So pi is the first minimum, 3 pi is the next minimum, and so on. And if we go back to the original question, you'll find that is where this is, and this is. At t is equal to pi and 3 pi. If we look at our y value equation, 1 plus cosine of t, and we sub in cosine of t is equal to -1, then we get y is equal to 0 for both of those positions, and that's where the acceleration changes rapidly. It changes from an acceleration of -1 to an acceleration of +1, as it's going down then up, with nothing in between. Okay, hopefully you found all that extra, the superfluous stuff useful. Hopefully it didn't confuse you, and I'm sure some of you probably just skipped to the answer. That's okay. Alrighty, part C, we've got this complex equation, 1 plus cis 2 theta multiplied by 1 plus cis 4 theta. That equals u plus iv apparently. And then we've got to prove that u over v is equal to cotan of 3 theta. Okay. First up, the right hand side's in a rectangular form, right? It has a real part u and an imaginary part v. The left hand side is a mixture of polar form and rectangular form, and it's needing to be tidied up a little bit. So if we expand the brackets first, we've got 1 plus cis 2 theta plus cis 4 theta plus cis of 6 theta, because when you multiply complex numbers in polar form, you add the arguments. And now we need to understand what cis notation stands for, because cis is shortcut for cosine plus I sine. So the 1, well, 1 is just 1, but the first term here, cis 2 theta, is cosine of 2 theta plus I sine of 2 theta. And that there is a rectangular form. Cos 2 theta is the real part, sine of 2 theta is the imaginary part. We do that for the other ones. And now we group the real and imaginary parts together. So we've got a real part in 1, another real part in cos 2 theta, cos 4 theta, cos 6 theta. All of those are real, and they add up to u. And then the other ones, the imaginary part, sine of 2 theta, sine of 4 theta, sine of 6 theta, they all add together like terms to make v. Okay, so the proof starts with left-hand side is u over v, which is equal to the blue stuff, 1 plus cos 2 theta plus cos 4 theta plus cos 6 theta, all over the green stuff, sine 2 theta, sine 4 theta, sine 6 theta. And somehow we need to prove that it all comes down to cotan of 3 theta. Okay, so the first thing that kind of hints in the direction you need to go with this is the angles. Currently there are no 3 thetas. We've got a 2, 4 and 6 theta. So how do we get these expressions into 3 thetas? We need to combine them in some way. The first thing I'm going to do is use the double angle formula to get the 6's down to 3's. And I'll leave everything else the same. Sometimes when you change multiple things in one go in a trig identity, you actually miss the answer. So if we leave the first stuff and then just go and change the cosine of 6 theta. Now again, I'm using the same formula I used earlier, that cosine of 2a is equal to 2 cosine squared of a minus 1. And this time it's not 2a, it's 6a. So cosine of 6a, 3 times the angle, is 2 cosine squared 3a minus 1. That brings in the 3 theta. It'll also take the minus 1 will take away the positive 1, because it seemed like we had extra terms in the numerator than the denominator, so that's quite useful. So cosine 6 theta, I'm going to replace that with 2 cos squared 3 theta, which the ones will cancel. And then the denominator, I'm going to work with the double angle formula for sine. There's only one option for that. That's the formula sine 2a equals 2 sine a cosine a, except in our case it's sine of 6a, 3 times the angle, 2 sine 3a cosine 3a. If you haven't worked with trig identities before, notice a common mistake that students make is that they see the 2 there, get excited and change it to a 6, but we're only changing the angles. The angles are triple, the structure of the identity remains the same. Okay, so sine 6 theta gets replaced as 2 sine 3 theta cos 3 theta. Okay, so I've brought in some 3 thetas. It makes sense to move all the other stuff to 3 theta, so now I'm going to work on these dudes together. There is a sum to product formula on the formula sheet that you can add two cosine expressions. It says cosine C plus cosine D, so I'm going to use that one now. Cosine 2 theta plus cosine 4 theta is 2 cosine of C plus D all over 2. That's 3 theta, because 2 plus 4 is 6, 6 divided by 2. And then we've got multiplied by cosine of C minus D all over 2. I just take the bigger one to be the C, so 4 theta minus 2 theta is 2 theta divided by 2 is theta. Do the same thing on the bottom, add the sine expressions together, so sine 2 theta plus sine of 4 theta. Go to the sine C plus sine D and take the C to be the biggest one. We get 2 sine of 3 theta multiplied by cosine of theta. And lastly, we can divide everything by 2, top and bottom, and we can factor out of the top and out of the bottom cosine of 3 theta and sine of 3 theta. That's our answer to the problem, by the way, but we just need to show one more step of working. Oopsies, close brackets too early. And top and bottom factors the same, equals cotan of 3 theta. Happy days. Catch you in the next video.